Yeah, it looks like maybe, let's see, I'm looking here today as well. Today is the 2nd. I'm continuing to wrapping up 1.3 because I just started 1.3 and I knew it was a big enough section that warranted 2 days. Yeah, so when I got started on 1.3, we're doing something about transformations. There's this oftentimes shifting, and there's an order to it. Which way is first? Okay, it's always left and right. So there's always a shifting left and right, and how do you recognize that? Just take some practice to see where that is. And then 2 and 3, steps 2 and 3 could be interchanged as to what do you do next, what do you speak next, and what do you do third. When in fact, on problems like, let's see if I've done these yet. Oh, I stand corrected. I just spoke something out of place. I just spoke something out of place, and I apologize. So we're not even there. That whole transformation, that's 1.6. And so 1.3 is looking at functions, and piecewise defined functions is what we ended up leaving you guys with, and creating equations from graphs, or graphing the pictures from the equations with the restricted domain. So sorry to have mixed you up with that other stuff that didn't make any sense to you. Probably thinking of my Math 27, which this is, maybe that's what's throwing me. It's not, you aren't Math 27. That's the typo. It should be 25. This is a correct booklet. That's incorrect. So anywhere you see Math 27, it should have been Math 25. Okay. So it looks like this is the last one that I finished with. Here I gave you the graph, and we came up with the equations. The next example would be produce the graph based on the equations. So that's what I'm going to do. Now, how I might go about doing these is, remember, this is a fancy way of saying the letter Y. So if I looked at the first one up here, Y, and make that equals, the statement over here is telling you what values of X that you get to use for that equation. So less than -3, how about -1,000? That's too big or too small of a number that I want to deal with. But yeah, -1,000 works. When I say too small or too big, if I put in -1,000 over here, and that's kind of a biggie number, then I'm off my grid. So I'm trying to keep on the grid a little bit. So what if I chose, let's say, -5? -5, that's less than -3. So even doing this is helpful. Here's your X and here's your Y. So I said -5, and now you do the arithmetic. So -5, the opposite of -5 is 5. Subtract 3. If I've done this correctly in my brain, without a mistake, without writing it down, it should be 2. So again, maybe this is needed for you guys. You go the opposite of -5, subtract 3. That's 5, subtract 3. That's where the 2 comes from. Now, I'd like to think all of you know that all 4 of these are lines. They're equations of lines. They're not parabolas or cubics or square roots or anything else. They're just lines. So if they're lines, this is y equals mx plus b. That's another way of looking at it. The y-intercept is -3, but the slope is -1. Now you got to be careful. You're going to go y equals mx plus b, because if I went and plotted -3 down here at the bottom and did the slope and connected the dots, you're apt to just make a big long line right here, and you're forgetting about the restrictions on the domain because you don't get the entire line. But I guess the point is they're lines. So let's connect the dots somehow. I got to find a second dot. So my suggestion would be always pick the endpoints, like -3 on this one, pick -3 on this one, and 0 on this. Now, because these don't have equal signs, in theory, you don't get to use them, but I'm going to use them with an open circle. And the open circle indicates it's not allowed at the, when you finally look at the graph. Where this one here would be a closed circle. So open, open, closed, open, closed. If both of these were right here, were equal, then you wouldn't have a function. Doesn't even matter if one sits on top of the other. It's the idea is you have two outputs for one input. You have, so you want to be careful. Open circle, closed circle. That's how I'm going to handle this. Okay, this would be -3. So I'll say closed, closed on this one. And if I put in -3 here, you go y equals the opposite of -3, and then subtract 3. That looks like it's going to be 0. But this would be open circle. Now I can plot the points. Let's see, -5, (2), and that's a closed circle. And -3, (0). That's open. Now,
-3, (0) is an open circle, even though it says less than or equal to.
Thank you for that correction. You're absolutely right. And I'm going to write over here to make sure this should be closed. You're absolutely right. I'll say C for closed, O for open. So thank you for that correction. You're absolutely right. So I'm going to put a solid dot right here. And then connect the dots. Now, connect the dots. Do I go down here? The answer is no, because I want less than -3, so I want to go this way. So, okay, the next one is this one. So I'm recommending the endpoints. Endpoints, endpoints, and here you need 2 points anyway. But here, -3 and 0. So I'm repeating -3, but I'm also including 0. But on this equation right here, so I'm going to go y equals -3 plus 3 is equal to 0. Y is equal to 0 plus 3 equals 3. Now, both of these are open. So both of them are open. So I'll say open here. -3 is 0. Well, okay, should be open because it's already got a closed one. So how do you do this, Jeff? Nothing. I mean, if I did a red here, you can't see it, like here. Not a big deal. Not a big deal. Blue indicates I'm going to use this one, solid here. But then 0,3 would end up being right here, and that's open. So maybe if I did it in red, that's open, and connect the dots. So this one's filled in, but with blue. And the blue is going to be this one here. That's the blue line. And this one here is the red. I think I got a couple other colors. Let's see, I've got orange. Let's see if this will work. Let's see, go over here, orange. Not a huge difference in color in orange and red, but let's see if we can try this. Y equals negative 2x plus 3. I'm going to try x and y. These ordered pairs is 0 and 3. 0 and 3. So if I put a 0 in here, that'll be 3. And that one's closed. And if I put a 3, this one's open. So if I put a 3 in here, so negative 2 times 3, that's negative 6. So I'm putting in 3. Okay, some of you are not seeing. Okay, y equals negative 2 times 3 plus 3 equals negative 6 plus 3 equals negative 3. So negative 3 goes right here. Okay, so with orange, I'm going to go closed. Okay, so right here, I'm closing up the open circle with orange. And then open would be 3 comma negative 3. So 1, 2, 3 comma negative 3. Open right there. And then and not a huge difference. I got purple though. Purple. Might look like blue, but it's really purple. Okay, pick 3 and pick something bigger than that. How about 4? And both of these are closed. So if I put in 3 right here, that's negative 3. If I put in 4, that's negative 2. 3 comma negative 3, so 3 comma, okay, so now the open orange becomes a filled in purple. And then 4 comma negative 2. And then connect the dots. And if I haven't made a careless mistake, then that should be the graph. And then if I said something like, okay, here's a question. Find f of x. Okay, so f of, let's say 1. Find f of 1. You're going to go and see what color you want f of 1 to be. So it looks like f of 1's got to be orange because there's 1. Or you go over here and say, where does 1 sit? Right in here between 0 and 3. So f of 1 would be, put a 1 in for x, negative 2 plus 3. So f of 1 should be right there. There it is. F of 1 equals 1. And then if I do f of negative 7, so you see, where does negative 7 sit? Not there, not there, negative 7. Oh, up here, less than negative 3. So I'm going to use this one, which was blue, this one, negative 7. So let's see, that's 3, 4, 5, 6, 7. Okay, so it's up here somewhere, but I don't want to just look at the graph because I did a kind of a crummy job connecting the dots. I want to find the actual equation, which is right here, and replace that with negative 7. So then you'll go the opposite of negative 7, subtract 3, f of negative 7, 4. The answer is 4. Okay, that's an example. I think I said, okay, some of your homework, work the ones that had these types of problems, which would be piecewise defined functions. Now, there's some other topics that we're going to get to now that were at the beginning of the homework set. And now this will help you wrap up 1.3. I'm not going to do this one. Unless I have time at the end of the day, I'll come back to this. And likewise here, if I have time, I'll come back to this. I'll come back to this page if I have time today. So the first thing we're going to look at is called symmetry. Symmetry. Now, there's two different ways of looking at symmetry. First way is up here, second way is down here. First way is up here, so symmetry. Now, if I did a circle centered at the origin, I would almost claim there's infinitely many concepts of symmetry. A circle is this very unique and perfect, in a way, figure. So there's symmetry this way. And when I say symmetry, notice that it folds up on itself. Same thing going this way. The axis, it's called the axis of symmetry. Also this way. So there's three very particular things that the author wants you to kind of consider. It's the axis of symmetry, so it's either y-axis symmetry, x-axis symmetry, or this interesting line. When I say interesting, we're only going to look at the one that goes up to the right through the origin. That has a 45-degree angle right here. That equation is y equals x. And they call that symmetry with respect to the origin. Origin symmetry, it sounds like a weird phrase. I've never heard it said that way, but that's true. Y-axis symmetry, x-axis symmetry, symmetry with respect to the y-axis. Okay, I get it. Symmetry with respect to y equals x, or the origin, because it goes right through the origin. And it has 45 degrees as the angle. Now, some of these problems, you're going to struggle with the graphs because you can't put it in graphing calculator just to look at the picture. Or you might not know what the figure looks like. And it may not even be a function, like this is not even a function. So like this one, you'd say, well, I hope you know that you can't even graph this thing the way it's set up. You can only graph something if it's y equals in your calculator. That's the only way. Well, it's the only way I'm going to teach. Later on in this course, there is another way to graph non-functions. It's called parametric equations. And it's usually the last topic I hit before the end of the semester. Anyway, we don't have that right now. So, gosh, I don't know. This kind of feels like a parabola, maybe, because there's a power 2 on one of them. Maybe you get that idea? But it's not a y equals parabola. So there's three steps to check for symmetry, and that's what they're asking. Algebraically, check these and determine whether it's got what's called y-axis symmetry, x-axis symmetry, or symmetry with respect to the origin. So I'm going to test every single one of these tests. I'm going to apply it to each one of these problems just so you can see what happens. Okay, so let x be negative x. Right here, let x be negative x. I'll call that number 1, right here, number 1. And if it turns out when it says equivalent equation, meaning if it comes back to be exactly the same as what you started with. When I put in negative x here for x, do I get exactly the original up here? I hope you see that you don't. I mean, the right-hand side's the same, that never changed, but the left-hand side's not the same. So number 1, I'm going to say no, NO, meaning there's not that symmetry. Okay, number 2. Number 2 says, okay, replace y with negative y, substituting negative y for y. So I'm over here. So I'm going to go back to the original. X equals parentheses. So up here is the original. Wherever y is, make it negative y. And then simplify. So when I simplify, this would be x equals positive y squared minus 1. Now, this one turned out to be exactly the same at the end. So these are the same. And so I'm going to say yes because they're exactly the same. And what that means is if you were to graph this, it would have symmetry with respect to the axis. Sort of like this. This isn't necessarily the picture. Could be. If you had a picture that looked like that, see how it goes right through the vertex in this case. That's got symmetry because it folds up on each other. So number 2 is a yes, and then finally number 3. Number 3 says, all right, take the x's and y's and make them both negative x and negative y, and then see what happens. So here's the x and y. I'm going to go parentheses equals parentheses squared and still a negative 1. So this becomes a negative x and this one's a negative y. And then what do I end up with on this one? I get negative x equals y squared subtract 1. And does it go right back to the original? It does not. So this one's a no. So the only symmetry you have is with number 2, which is then, say, symmetric with respect to the x-axis. So you could say, oops, x-axis symmetry. Okay, the next one, doing the same thing. If I do number 1, I'm just going to go in and put a negative x here. Squared plus y squared is equal to 1. And I think it can look like that's the same thing. So I'm going to say yes, the same thing. 2. 2 says put in negative y for y. Leave everything else the same. So x squared plus parentheses negative y. And as you can see, if I square a negative, it right back to where I started from. So this one's going to be a yes as well. And number 3 says replace the x and y with their opposites. And that becomes x squared plus y squared equals 1. And that's a yes as well. So this one satisfies all of them. And it turns out to be a circle right here. It'll look like this with radius 1, centered at the origin. So that is the picture of this one with radius 1. And now this one here, final one. That means I'm going to let x be negative x. Simplify this. Does that look identical to the original? And it doesn't. So I'm going to say no. Number 2, let y be negative y. So I'll go back to the original. So this is negative y equals 2x minus 1. Of course, that's negative y equals 2x minus 1. Well, the right-hand side's the same, but the left-hand side's not. So this is a no. And finally, number 3, let both x and y be the opposites. So negative y equals 2 negative x, subtract 1. Negative y equals negative 2x, subtract 1. Now this is close. If I multiply through by negative 1, change the signs to everything, Oh, it's still not the same. See, I missed it right there. So it's all no. And so you'd say there's no symmetry. Well, there might be symmetry, but it's definitely not with respect to the axes or that special line, y equals x. Now, the other way of determining symmetry turns out to be odd and even, whether the function is called odd or even. And then if it's even, there is symmetry. If it's odd, there is symmetry. It's one of these. If it's even, it's one of these. If it's odd, it's one of these. And then the only other option you have is it's neither. It's not odd, it's not even. That's what you'd say. Not odd, not even. So the formula that's describing even would be this one here. And what does that mean? That means if you let x, well, right in here, if you make this negative x, let x be the opposite, do you get right back to where you started from? That's what it's saying. So if I went f of negative x, and the right-hand side is in fact f of x. So this statement right here, that is in fact f of x, the original. That satisfies the conclusion right here. So this one is even. And what that means is if it's an even function, it has y-axis symmetry. If you graph this, well, I think all of you know that this is a parabola. If you graph this parabola, it's going to go right through, the vertex is going to sit on the y-axis. That's where it's going to happen. True or false, all parabolas have a y-axis symmetry. No, I said all. No. You could have a parabola that has a vertex that sits off the y-axis and then doesn't have y-axis symmetry. It has a line of symmetry, but it's definitely not the y-axis. Okay, if I do this one, well, Jeff, this is a parabola as well. This is a parabola. These are both parabolas. Okay, that one's even. This doesn't necessarily mean it's even. So you have to go through the process and say g of negative x, 3 parentheses negative x squared. You see, that's not exactly the same. Nope, nope, no. So it's not even, not even. Okay, what about this odd thing? You know, maybe it's odd. What this is saying is if you do the negative x inside everything, if it turns out it's the opposite of the original, opposite, that means all the signs changed. Here's a sign. So to be odd on this one, each one of these would have to have a negative in front of it at the end. Only one of them got it. So it's not odd. So not odd. So I'm going to say not odd, not even, not odd. So the answer would be neither. That's what you'd end up saying. So the answer here would be even. I said it wrong. The answer is neither. The answer is neither because it didn't turn out to be odd or even. So you say neither. Okay, this one here we go. H of negative x. Simplify. Now I'm going to, you don't have to do it this way, but if I factored off a negative sign off both of these, And what's in the bracket is the original right here. What's in the bracket is the original. So I'll put that in brackets so you can see that. So what I was telling you is you just notice if all the signs changed. They did. See, the signs change from here to there. You can stop right there because it indicates that it's odd. I'm just showing you by proof that, look, it's the opposite of the original. That's what I'm saying. It's the opposite of the original. So this one's odd. Now, if it's odd, it turns out to have symmetry with respect to the origin. So with respect to WRT, with respect to origin. And the last one, so I'll go V of negative X. Simplify, let's see, that would be 2x to the, okay, so it's not negative. Whenever you take a negative raised to an even power, that means you have that many negative signs. So 6 negatives make a positive, even number. Over here, do this first, don't do that first, do this first, powers first, and then multiply. So this ends up being negative 3x squared, and then plus 6. Does this look identical to the original? And it does. So even. So you'll have some problems. The first, I think towards the first part of the homework set, some problems that will ask you to test for symmetry or determine whether or not the functions are even or odd. Now, even or odd talks about function. Just make sure you understand that, because this is all function language here. Symmetry doesn't necessarily mean that they're going to be functions up here. Okay, flip the page. The next concepts you're going to learn is about if a picture, a function in particular, is what they call increasing. In other words, if you go from left to right, does it look like it's falling? Or that's decreasing. Increasing would be rising. Constant means there's like a horizontal line that goes this way. That's constant. Doesn't change. And then the other topic that we'll see is this whole idea about maximums and minimums. Your author has formal definitions of everything in here. I'm going to point it out to you. Then I'm going to paraphrase everything to kind of help you have a little memory device. Hopefully it does help. Increasing, decreasing. So on page 182, page 182, down at the bottom. Formal definition with some pictures here, but formal definition. It starts the English language mixed in with the mathematical language sometimes throws people who are just beginning through this journey until you get to a place where you can talk like calculus. We're grooming you for calculus. You get a better understanding. Bonnie could probably talk to you about that as a student. She's in second semester calculus here at SRJC 1B. And the more she sees it, the more people around her talk the same language, the easier it becomes. So understanding this statement, I would think Bonnie has a better understanding of it now, or could at least think through it, versus say a year and a half ago when she was going through this journey. I see the word increasing. They put this in bold. Now, An interval is like an interval notation if you thought about it. There's no interval notation listed up here. But an open interval would indicate a parentheses, not a bracket. And all of you should be very familiar with that notation, interval notation. Also, open interval would indicate no equal sign. So I don't see any equal signs in here. This is like a conclusion, and this is like the beginning. It's like an if-then statement. If you're moving on to calculus, through calculus, you might be taking a logic class. We teach one of those here at SRJC, a logic. There's these if-then statement. If this happens, then this is the conclusion. They're putting the conclusion first before the if. So if I looked at the if first, this says these are y values. The f means the y values. F of the first x is, that means the first y value is less than the second y value, as long as the first x is less than the second x that you're trying, and that's for any number on that interval, then it says it's always going to be increasing, and the picture's going to look like this. See, it's always rising right here. And so they give a demonstration that on the axis, you can see that the x here is to the left of this x here. That's what it's saying right here. The first x is to the left of the second x. It is. And if you go right up to the picture, that y is below or less than that y. It is. Therefore, every point along the curve right here is going to act that way. We say this function is increasing between, notice the open circles. You guys see that right there? It's increasing from wherever this is to wherever it starts turning. And that's the key, is the turning. So now if I look at this one, well, even this one right here, I know, and you guys are going to get it easily too. That's increasing until you make the turn. Instantaneously at that turn, right there at the peak. I don't know if it's increasing or decreasing. It's not. It's like a tie. So that's why we leave an open circle, like an open interval. So from here down to the bottom, to the valley, it's decreasing. And then from down the valley forever, it's increasing. So there's two intervals where it's increasing. And I show you how to write that with a union symbol, the way you join it. And there's one place where it's decreasing on this one. Let's see. This one here, that's constant, increasing. So if I want the interval for which it's constant, it's from -infinity all the way up to 0. Both of them are parentheses. And I'm going to tell you right now, there's going to be a number of you that are either not getting it or you're not just memorizing. There's no brackets. Some of you are going to put brackets on it. I know it. So watch out, be careful. The other thing to be careful of is it's always x values that you're being asked for. Intervals for which it's increasing, decreasing, they're always focused on the x values, not the y values. So just keep that in mind too. And I'll show you those with some examples today.
Jeff, can you repeat what you said there's no brackets on?
The intervals for which it's increasing, decreasing, constant. When you see interval right down here, interval notation. So the interval notation, typically you have some choices based on whatever you're looking at. You either got parentheses or brackets.
Yes.
Oh, you're okay with that?
Yeah. So you're saying there's no brackets on intervals that we are determining is increasing or decreasing or remaining constant?
And that's because right there, the word open right there means parentheses. I'll use the P for parentheses
Okay.
because I can't write the whole thing. Not brackets,
Okay.
because it says it's open. The other reason is you can see that there's no equal sign anywhere. That's a strict inequality. So that's like an open circle or a parentheses. These are all parentheses as well. Yeah, so remember, it's always open interval, parentheses only. So when I look at, when I look at the first one right here, gosh, I have to look at the picture. This one's probably more, I'll start with this one. This is more interesting here. I'll graph it. That's the way that I'm going to suggest you guys do it, is graph it first. Y equals, get rid of that, x squared, zoom standard, zoom standard. I didn't do that. Zoom standard. Yeah, that's better. So decreasing, increasing from left to right. You've got to know, though, where it makes its turn. You have to know that. So here it's pretty obvious it's at the origin. I think it's obvious. But instead of saying it's obvious, don't guess on the count, because sometimes it's not going to be obvious. Most of the time it's not going to be obvious. So you have to know how to find what's called the vertex. And that's using keystrokes. So I'm going to show you. Once you graph the you put the graph in the calculator, there is a place right here. It's called calc. There's a blue word or phrase called calc. It's the trace button, but to get to the calc, you have to press the second feature right here. So I'm going to press second and the trace button. And you've got a selection of things to consider. The one that you want is either minimum or maximum for us. Minimum, maximum. Now, how I remember it as a student, minimums are valleys. Minimums are valleys. Maximums are mountains. So I'm going to do minimum. Second, trace, minimum. Now, there's two ways of using your TI 8483. There's two ways of doing it. I'm going to teach you the way that I think that most students will not make the common mistake. Now, some of you have done this before and you're comfortable with doing the toggle. You know, it's like toggle here. See, left bound meaning I want to try to get the cursor to the left of where I'm wanting to find. So toggle, okay, that's far enough left. Some of you are comfortable with this, and then you hit enter and it says right bound. So then you just kind of keep toggling until it turns maybe about there and hit enter. And notice there's the flags. The flags are trapping what I'm hoping to find, which is the origin. And we always say enter for guess. Okay, and then we'll talk about what all those crazy numbers are. We'll just talk about that later, in a moment. But the way I'm going to teach you guys is this one, minimum. It's the same problem, minimum. And the reason behind it is a number of my students, when they watch the cursor, they're only thinking up and down. The cursor, I don't know, mentally, brain-wise, you're not looking left and right, you're looking up and down. You're watching how it goes. Even the picture of the graph, it seems to be easier to see it up and down, not the left and right. And especially if the picture goes off the graph somewhere, off your screen, and it jumps back over, it throws a lot of my students. So here's my idea. Take a pen. Well, I'm going to take a pen, felt pen. Don't do a Sharpie. Take a pen and put a dot right there. That's what I want to try to find. And the calculator is asking questions. And it says, where's the left bound? That means pick a number to the left of the blue dot. Pick a number don't stay on the screen. Stay on the screen. Don't go and say, hey, negative 1,000. It won't like it. So somewhere over here, like, gosh, I don't know, negative 5. So I'll press -5. And then you'll see a flag right here, and it's not going to look anywhere this way. It's going to look this way because that's the way it's pointing. It's going to look for the lowest, the minimum, the lowest y. It's going to look for the lowest y value is what it's really doing. But you're pressing X values to kind of put the boundary in, the flags. And then the right bound, pick something over here. How about 3? Sure, 3's right there. 3's to the right of that. This. Some of you might have a TI-80 for color screen edition, color screen. And I think those models actually put in color walls. They'll actually put in maybe not a dotted, it actually puts in maybe a red wall. And what that's doing, instead of the flags, it's trapping this part within the walls, and it will focus on looking for the lowest, which it should be right there. That's the lowest. Hit enter for guess, and then we get some crazy numbers again. Different ones than last time, but crazy numbers. And notice the cursor's blinking where I expect it to be, which is the origin. So what's the crazy? Anybody seen that before in a previous class? I'm curious. Speak up if you have. Just say, yeah, I have. In a previous class, like a 155 or 156 class. Ever seen anything that looks like that with the E's? Nobody. Interesting. My 155, we always find that because I use the Texas Instrument calculators exclusively. So, well, this is scientific notation. E means scientific notation. It's the same thing as going like this one here. That's 2 point, I'll just use 9. And that would be times, and that would be 10 to the -13 power. And in your baby algebra class, your maybe even arithmetic. So you should know scientific notation. That's not something I'm reteaching. You know you're going to move that decimal either left or right. And gosh, -13. I mean, you can investigate it, but that's going to go left. You can think like negative powers go left. So if I move this to the left 13 places, look how small that's getting. It's trying to say 0. Why the calculator just doesn't say blasted 0, 0? You call them. You call Texas Instruments. 1-800-TI-CARES. There, I just gave you the phone number. 1-800-TI-CARES. You're going to get people on the phone and just say, my instructor called or told me to call you guys and ask, why is it when I do a problem, and show them when I get a problem like this, my calculator doesn't come up with 0, 0. Why not? Can you fix it for me? I don't think they can. It's old technology. You just have to interpret it. So it's up to you to know that this is saying that's 0, that's 0. Anything with the E negative typically is going to be 0. All right, now with all that meaning, I know I'm looking for decreasing right here. This is decreasing until that X value right there. Decreasing until that X value, which is 0. So decreasing is going to be from -infinity, all the way to 0. And this is when you're going to put parentheses because it's an open interval.
Didn't we do the second problem first?
Pardon me?
Didn't we work on the second problem first?
Second problem. Oh, thank you. Yeah. I understand what you're saying right here. Yeah. Thank you. Okay, increasing is going to be from 0 to infinity. And constant means there's a horizontal line and there isn't one. So you're going to say no, no, or none, no, or none. Okay, in your textbook as well, you will find topics that's called relative mins and maxes, absolute mins and maxes. All right, these are Y values. Those are y values. So all of these are going to have, if they have one, it's going to be always y equals. It's not an interval, not an interval. It's going to be a y equals because it's a number. If you just put down a number, let's say group quiz, and you're showing me all your work, if you put down a number without the variable, you're not going to get it right because I don't know if you know that it was a y or an x. It's always a y. So the question is, what are these numbers, if there are? Relative, by the way, it's, I'm going to use the word turn. So relative, based on the definition, I'm just giving you an easy paraphrase on my end, is where there's turns, it's relative. So wasn't there a turn on this one, by the way? Yeah, there's a turn right here. So the y value right here is a relative minimum. So you go y equals the 0 at that ordered pair. The ordered pair is 0, 0. So the y, that's the lowest, by the way. See, if I said it's the lowest out of all of them, that's the absolute minimum as well. So not only is this a minimum because there's a turn, it's the absolute minimum, and you have to include that. Now maximums, here, there's got to be a turn. Is there a turn? Is there a mountain? Maximums are mountains. Yeah, so you're going to say none here for relative. Absolute maximum, that is the biggest, highest y number that you might see on the graph. And there is one, according to me, I don't know what the author says, but I'm going to say there is, and it's y equals infinity because it goes on forever. It doesn't stop at the top of the screen. It goes on forever. I'm going to skip this one. This is just a line. I'm going to skip that one. I'm going to go these two. I'm going to do it on time. I'm not going to do that one. I'm getting close. Yeah. Bonnie, I might use up quite a bit of this time here today. I want to finish these guys up, so we'll see what happens.
Go for it.
I'm going to put this in my calculator right here. All right, so I've got a, I just double checked and it looks right in terms of what I've typed in. I've got a image that's kind of crummy because it's not giving me any real idea. I'm hoping that all of you know what kind of picture this is because of the previous class before this class. Because you would have looked at these kinds of pictures. It's called a parabola because it's a power of 2. It's a parabola. I can't see what's happening on the vertex. Anybody have an idea whether this thing is a mountain or a valley? Anybody have an idea whether it goes like this or like that?
Mountain.
Correct. How come?
Negative, the -2 in front.
Good for you for remembering it. Exactly. Good. That means somewhere up here, there's got to be a turn off my screen. So I want to adjust my screen so that I can see a parabola better. I'm going to go into Window. This is the way I'm going to do it. And I'm going to go higher because I'm pretty sure that the parabola is turning somewhere off the screen higher. So I'm going to change my Y max to something higher than 10. How about 20? And hit graph just to change that one only. Nope, I got to go higher than that. Let's see. Negative 4, give me a second, 4, comma, 15. I'm gonna check something here. Oh, okay, I got a mistake, I realized, and some of you might have seen that and didn't tell me. That's okay. I knew I should have had the vertex by now, but let's see, delete. Okay, let's try this again. Yeah, it didn't like that. Okay, that's better. Even at Zoom standard, you wouldn't have seen it, but now I can see it once I raised it to 15. That's much better. Now I can find that vertex because that's what I need to answer most of these questions. So second calc maximum, which is number 4. Left bound, I'm going to pick something to the left of this vertex right there. I'll pick over here maybe negative 2. Right bound, something over there like 9. I'll hit enter to say okay. And doggone it, they're not giving me what I expect. You're right. I have no idea why they're not just saying 4. No idea. It's supposed to be 4 comma 15. Now, most of you would realize maybe from a previous class that the vertex was easily identified, and we're going to look at quadratics again in chapter 2 coming up. Deeply more, like larger problems. But right now, vertex is 4, change the sign, comma 15, keep the sign. So that's the vertex. But decreasing, okay, so decreasing starts, these are x values. That's at 4. This is at 4, and it goes to infinity, and it's always open parentheses. Increasing, negative infinity up to where the top is, and again, it's the x value. In constant, there is none. Relative minimum, that means there's a turn. These guys are turns again, turn, turn. There is no turn for the minimum. That would be a valley. So you'd say, nope, nope, none. But yes, there is a turn right here. And so the y value there is 15. So you're going to go y equals 15. And it turns out it's the tallest one as well. So you say absolute. Hey, Bonnie, do you remember in your 1A and 1B, do we use absolute or global? Do you remember the word?
I think it's global.
So in your calculus, you might see the other word, global. For us, we're using absolute. And the absolute minimum would be negative infinity, negative infinity. I'll go squiggle. Should have done it in the other one. Bonnie, I'm going to leave this one for you to do in your own session, okay? Or anything else that's like it. Leave you guys to read this. It's called the step function. We do a little bit of it in calculus. It looks like a little staircase, but I'll leave you to read it. See me outside of class if you want to know more about it. It's called the greatest integer function. I want to get over here to what's called this formula right here, the difference quotient. That's what I'm headed towards. And so one of these I'm going to do, and Bonnie's going to do the other one. So I'm going to do this one. And Bonnie, you can work on the other one in your session. Okay, this one here. Function. Okay, this should be elementary for you guys, meaning you're just going to replace x with 0, so it's 0 squared, subtract 3. That means when x is 0, y is negative 3. That means when x is 0, y is equal to negative 3. It's an ordered pair. In like manner over here, this is easy. You go 2 squared, subtract 3, f of 2 equals 1. This one here, just be careful, the negative. You go f of -3, it's parentheses -3. That's 9 subtract 3. F of -3 equals 6. Now it starts getting weird. You're replacing the x with other stuff, not necessarily just a number, just other stuff. So this one here, you're just making the x all h's. So you go h squared, subtract 3, nothing else to do. Right now it's meaningless. It's plug and chug. This one, a little more challenging. I'm going to put the x and a subtract 2 right in here and there. And x subtract 2, that means parentheses on this one, x subtract 2. And don't forget the subtract 3 is sitting there as well. And then we're going to want you to simplify, meaning do a little bit of algebra. Write this down twice. Don't make the common mistake by squaring and squaring it. That's the common mistake. Write it down twice in FOIL. Collect like terms. And then you're done. And then finally, this one here. This one's going to take a little bit of work. We're going to go x plus h right here. X plus h right there. X plus h right here. So we got x plus h subtract 3. And you're done. Now the last thing, and then I'll be done for today. The last thing, now this is called the difference quotient. Bonnie, where was this used in your, your 1A class? Because that's where it's usually found. What'd you use that for? Do you remember your 1A?
Sounds like you remember, Jeff.
I do.
It was towards the beginning of the 1A. I don't remember which
It
section.
was. It was. Okay, so to remind you, Bonnie, see, even Bonnie forgets sometimes when she does brand new stuff and she doesn't use it, you kind of lose it. But if I said to Bonnie, you use it to help you find the slope of tangent lines.
Yes, that's
along,
right.
Along with limits.
Definition of the derivative.
Right. So now it comes back to Bonnie, and if she had to do it, she would know how to figure it out. You guys are just learning the stupid little formula, and then in 1A, you use this along with new concepts to do something. So you'll see that probably about the second week, like Bonnie said, of calculus. So what am I doing? I'm using this, and as you can see, f of x, there's my f of x. That is going to go right in its place right there. So I'm going to do that first. I'm going to go rewrite this right here. Now I'm going to leave this alone first. Minus f of x is all of this. So I have to remember to put parentheses around that. And the h I just leave alone. The hard part's this one. Well, the hard part, well, not a hard part. A few of you are going to forget to put the parentheses around, and then you're going to get it wrong. A few of you are going to forget it. You just remember to put like parentheses or whatever's around here, brackets, because you got to distribute the negative to everything to the right. Okay, this is the hard part. F of x plus h. Well, guess what? That's the same one I used over here. Look. F of x, that's the same one right here. That's all I'm doing is the same thing as I did here. So you got some work to do, which I did it over here already for you. This right here is what you're going to replace for f of x plus h right there. So the ultimate, well, big long, here's the h, here's the negative, parentheses, x squared, subtract 3. That's sitting there. This on the previous page turned out to be x squared plus 2xh plus h squared. And there was still a negative 3, if I'm not mistaken. Yeah, there's still a negative 3 sitting right there. And now what I'm going to do is distribute and collect like terms. Distribute and collect like terms. Distribute and collect like terms. Now notice the x squareds go away. Hopefully you see that. You see that when I distribute? That goes away with that. Oh, that's nice. Oh, when I distribute the negative to the negative 3, this is going to go away with that. That's going to be a positive 3, negative 3 gone. So this will always happen, by the way. You'll know if you made a mistake if you didn't make everything go away without an h. The only thing that's left in the numerator has to be an h part. And if there's not, you made a mistake somewhere. There's just the h. Okay, so what's left is terms that have just the h. So I know I didn't make a mistake because there's just h's everywhere. And the last thing is you factor off an h, and up here you go h, and you get 2x plus h left over, all over h. These h's go away, and whatever's left, which in this case is 2x plus h, is your answer. And you have to remember statement h just can't be 0 because h is in the denominator to begin with. H, no, there it is right there. H just can't be 0. This is a bigger one. Bonnie can go through this today in her session, and this will take some work. So I'll suggest Bonnie to consider that. And there was one other one over here, Bonnie, you might want to, if you got time today too. That's something for you guys to work on, or any questions they might have. I'll leave that up to you, Bonnie, okay? So I'm done. That took a lot of time. 1.3 was a big section. The other ones are not so big going forward. It doesn't take as much time. So no baby quiz today. That's all I got for you. I'll stick around for about 2 or 3 minutes before my next class if you have personal questions. Otherwise, Bonnie's may have already headed to her Zoom class and you can go meet her over there. So then I'll see the rest of you on, today's Tuesday? It's Thursday. See you on Thursday. You got a question for me, Bonnie, before this last Sergio goes? No? So you can go off to the room and you're
I was
there.
just switching over. Yep, switching over to my next Zoom meeting.
Okay, see you later.
All right.